All right, I think we'll get going. Hello, welcome everyone. I'm really excited to welcome you all to the Sci 113 Science and Society Speaker Series. My name is Dr. Marcia Graves. I am the director of Sci 113, the first year seminar in science, and I'm also an associate professor of teaching in the Department of Microbiology and Immunology. So I'm very excited to welcome you all to our very first seminar of this term. Before we start, I would like to open our speaker series by respectfully acknowledging that I am personally a settler joining from UBC's Vancouver Point Grey campus, situated on the unceded traditional and ancestral territory of the Musqueam people. I feel very privileged to have spent actually a large part of my learning journey here on these lands. I was once a UBC undergraduate student like you. And these lands are a place of learning for the Musqueam people, where traditional stories and knowledge are passed down through generations. And I encourage you all to kind of take a moment to really connect your learning to this place, to this land, and just reflect on that privilege that we have to be here and engage in our learning together. So a little bit of just logistics about the Sci 113 speaker series. We have a total of 6 lectures for you this term as part of our course, and we'll be hearing from a bunch of different scientists from different disciplines, and the goal is to really hear from a variety of folks with unique journeys in science, from different perspectives, approaches to science, and just to hear the very diverse ways in which scientific research can be done. So just a few guidelines for students. This lecture series is always scheduled on Thursdays at 12:30. And if your schedule permits, we really encourage
We're talking
you
about
to
learning
join live.
modes right now.
Just gonna make sure that your mics are muted. So yeah, just keep those mics muted while the speaker is giving their talk. And so, yeah, we do encourage you to join live. So it's great to see a nice big audience here with us today. So thanks for joining. For all students, whether joining live or watching the recording later, during the talk, we encourage you to think of questions that you would like to ask the speaker, and those that are here live. There will be time at the end of our speaker's presentation today to ask those questions either in the chat, being mindful of our respectful behavior, and you could also raise your hand using the Zoom function as well, and we'll do our very best to address each question at the end. You're expected to complete the speaker series worksheet, and for this first speaker, you're all required to complete the worksheet for Dr. Kunimoto, who I'll introduce in a moment, and that is due this Saturday at 10 p.m. For the remaining lectures of the term, we'll have 5 more throughout the term, and you'll be expected to complete 3 more, so of your choosing. All right, without further ado, it's my absolute pleasure to introduce our first speaker of the term, Dr. Michelle Kunimoto, who is a graduate from UBC in the Department of Physics and Astronomy. And after her PhD, she went on and did a postdoctoral fellowship at MIT's Kavli Institute for Astrophysics and Space Research. When Michelle was at UBC as an undergraduate student, in fact, she was once a Sci 113 student, just like yourselves, in her first year. And interestingly, she went on to do undergraduate research and had the extraordinary success of discovering new exoplanets, which is pretty amazing as an undergraduate. Dr. Kunimoto specializes in exoplanet detection, characterization, and demographics, where she led MIT's Quick Look pipeline team and discovered actually thousands of new planet candidates, which we'll get to hear all about today. Additional accomplishments include being named to the Forbes 30 Under 30 in Science list in 2017. And I was really excited to learn that Dr. Kunimoto was coming back to UBC, where she has now taken up a faculty position back in the Department of Physics and Astronomy here at UBC, where she first started her career. So please join me in welcoming Dr. Kunimoto. We really appreciate you joining us today.
Yeah, thanks for having me. Could you enable screen sharing, please?
I sure can. Let me look.
Okay, there we go.
There you go.
All right, so yes, today I'm going to be talking about A Planet Hunter's Guide to the Galaxy. And it's a little bit about my research, my journey through astrophysics, and I'm also going to talk at the end about how to get undergraduates involved in exoplanet research. So to start off, there was a really nice introduction, but I want to talk a little bit about my background. I'm actually from Abbotsford, which is about 2 hours outside of Vancouver. And when I was growing up in Abbotsford, I had no idea what I wanted to do. I had no idea I would eventually move to Vancouver when I was 10. And it wasn't until I hit high school that I started to think about doing astronomy. And the reason I wanted to get into astronomy was actually because I'm a huge Star Trek fan. My dad introduced me and my brother to Star Trek when I was in high school, and it just really captured a sense of curiosity I had for the world and to search for potentially habitable other planets. And so, as it was mentioned, I stayed here in Vancouver. I did my undergraduate and my PhD degrees at UBC, where I got a lot of research experience looking for planets that I'm going to talk a bit about. And yes, I was a Science 113 student in my first year. Then I worked at MIT on the TESS mission, which is NASA's current mission to find new planets, and I'm now a professor here at UBC. I just started in July. So it feels really cool to be coming full circle and to be back here at UBC where I started my career, as Marcia said. So speaking about my research, what do I study and why do I study it? My research is all about exoplanets, and exoplanets are planets that are outside of the solar system. Exo means outer, so an exoplanet is outside the solar system. And so far, we have found thousands of exoplanets. Our universe appears to be teeming with them. Statistically speaking, every single star that you look out the next time you go outside, and hopefully there's not a lot of light pollution from Vancouver, every single star has at least one exoplanet orbiting around it, and likely many more. And it's by looking for these types of planets and finding more of them that we can help answer some really big questions that have faced humankind for centuries. And I think the one really, really big question that everybody here has probably asked themselves at some point in their lives is that really big question. Are we alone? Is there other life out there? How common are planets like our Earth? Now, the image that I'm using in the background here is an image of the Earth. It's the pale blue dot. It's an image taken of the Earth from Voyager 1 spacecraft several decades ago. And I think better than any other photograph, it really captures that sense of curiosity we have to place our place in the universe in context. But more generally, how did we come to be? How did planets form and evolve? Why does the solar system look the way it does? And is that typical, or is our solar system very rare? There's a lot of physical processes that go into why some planets are more common than others, and that really gets into the physics of astrophysics. So I try to study exoplanets and answer these really big questions in 3 major ways. The first one is to find new exoplanets. The more planets we find, the better we understand their diversity, the better we can understand, all the possible outcomes of planet formation and understand if our solar system is common or an exception. I also characterize exoplanets. So once we find a new exoplanet, we can better understand its properties. We can better understand the temperature on that planet's surface, the size of the planet, the mass of the planet, what it's composed of. And we're now in the era where we can also characterize an exoplanet's atmosphere. So we can actually tell what molecules are in another planet's atmosphere, even though they are hundreds of light years away. And thirdly, I look for trends in exoplanet populations. So once we have a really, really big number of planets, we can start asking which ones are the most common, which ones are less common. And that tells us something about the efficiency of planet formation. Planet formation likes to form some planets more than it forms others. And so that helps us understand the origins of our own solar system. So to start off, how do we actually find exoplanets? And I'm going to introduce a little bit of a history lesson by going back thousands of years to when we knew of the very first planets. The first planets we knew about were the naked eye planets because we can see them with our own eyes if it's sufficiently dark enough. And these are Mercury, Venus, Mars, Jupiter, and Saturn. And actually, observations of these naked eye planets go back thousands and thousands of years to the ancient Babylonians. And our observations of these objects are one of the reasons why astronomy is considered the oldest science. And then, of course, we have the Earth, which is the planet that we live on. But it wasn't until a few hundred years ago that we started to find planets in the solar system with telescopes. Now, these ones you can't see with your own naked eye because they're quite a bit farther away, so they're too faint to see. But if you use a telescope, even in just your backyard, you'd be able to see these planets. In the 1950s were the first years when exoplanet discoveries started to be made, but all of them turned out to be flukes. The data just wasn't good enough. People were, hoping to be able to find exoplanets, but technology was just not there to find them. And actually, the concept of finding another planet around another star was a really, really taboo topic. I wasn't, of course, around in these very early days of exoplanet hunting, but I do know some people who were around in the 60s and 70s. And in those early days, the concept of finding an exoplanet could get you thrown out of a conference. Like, people just wouldn't believe that it was possible because these are so far away and so small and so faint compared to their stars that it's really, really difficult to find them. You can't simply use a backyard telescope to do that. So astronomers had to think of more clever ways that they could find a planet beyond just using a simple telescope to do so. So in 1992 was the very first discovery of exoplanets. And I want you to pause for a second and just realize we've known about planets for thousands of years, but exoplanets have only been known about for about 30 years. So planet hunting makes astronomy the oldest science, and exoplanet hunting is one of the youngest and fastest growing sciences within all of astronomy. So Alex Wilson and Dale Frail made incredible history by discovering the first ever exoplanets. And they pioneered a technique known as pulsar timing. And this is the first method I'm going to talk about today. So with this method, pulsars are pulsating radio stars, and they rapidly rotate and emit radio waves. You can kind of think of them like an enormous lighthouse beacon in space. And so as it's spinning around that lighthouse beacon, if it's facing the Earth, we can record a measurement from that pulsar. We get this pulse, this emission, and we will measure this every few milliseconds or every few seconds, depending on how fast the pulsar rotates. And they're actually so consistent with how fast they rotate that they're considered the most accurate clocks in the universe. So let's say that we have a planet in orbit around that pulsar. Well, the pulsar is not going to be completely stationary as the planet orbits around it. What they actually do is they're both orbiting around the common center of mass of the system. So because the planet is gravitationally tugging and pulling on that star as it orbits, it's going to cause that pulsar to wobble very, very slightly around the center of mass. Essentially, what this means is that sometimes that pulsar is going to be a little bit farther away from the Earth than at other times. And those emissions are going to have to travel a farther distance to reach us. And so we'll measure that emission from the pulsar a little bit late. At other times, that pulsar will be a little bit closer, and so we'll receive that emission a little bit early. And so by simply looking at how early or how late these pulses are received at Earth, we can tell that there's some small body in orbit around that pulsar and causing it to wobble as it orbits. And because pulsars are typically so accurate, so precise and consistent with how they rotate, we can actually find objects that are as small as 10% the mass of the Earth with this method. Now, 1988 was actually a year that had potentially the first exoplanet discovery. This was several years before the pulsar discoveries. But one of the reasons why these weren't considered the first exoplanet discovery is because their planets were not confirmed until many years later. But what a lot of people don't realize is that this specific exoplanet discovery was actually made by a Canadian team of astronomers based right here at UBC, as well as UVic. So Gordon Walker, Stevenson Yang, and Bruce Campbell were Canadian astronomers at UBC who, may have found the very first exoplanets, but their published discoveries didn't receive confirmation until 2002, which is why not a lot of people realize. But it's really cool just to think that UBC has actually had this incredible early advancements in exoplanet hunting, and they also pioneered one of the most successful detection methods to date, which is known as the radial velocity method. So this is the second method I'm going to talk about. The idea behind this one is every star has a spectrum. And this is what I'm showing here for the sun as an example. And a spectrum is basically the whole collection of visible light that we receive from the star in different wavelengths or different colors. And you can see that there are these black lines everywhere. So these are wavelengths where there's some molecule in the sun's atmosphere that is absorbing light at that wavelength. And therefore, we're not receiving any light at those colors. And so every single star has its own spectrum. It's kind of like how every human being has a unique fingerprint, but this is how we can tell what molecules the sun is composed of. So how do we use these spectra to actually find exoplanets? Well, as a star is orbiting, and remember, if it's got a planet around it, it's going to be wobbling very, very slightly around the center of mass of the system. As it's moving away from the star, or away from us, the observer, the light from that star is going to be shifted to the red end of the spectrum through something called the Doppler shift. And as it's moving towards the Earth, the light is going to be shifted to the blue end of the spectrum, also through the Doppler shift. And so we can see that Doppler shift by how much those dark spectral lines are actually shifting. And we can relate the amount of shift to the speed of that star. It's very similar to if you were to stand on a sidewalk and hear an ambulance go by, and you can hear that the sound waves are changing in frequency. As it comes towards you and as it moves away from you, that ambulance siren is going to sound very different. And that's because of the Doppler shift. So this is the exact same thing, except instead of sound waves having their frequency shifted, it's light waves that are being shifted. But most important thing to remember about the radial velocity method is just how small of a change of speed that you can tell that a star is moving at. So currently, typical instruments are able to see a change in a star's motion of only 1 meter per second. And the absolute best from the last few years of technological advancements have been able to see tiny changes of movement of only 20 centimeters per second. Now, these are stars that are dozens to hundreds of light years away, and we can tell that it's changing its motion by 20 centimeters per second with this method, which is pretty incredible. I will note, though, that if we want to be finding potentially habitable planets like our Earth in a year-long orbit around a sun-like star, our Earth causes our sun to wobble only about 10 centimeters per second. So we want to be able to reach that with the radial velocity method. We're not quite there, but as we continue to improve our instruments, hopefully we'll be able to make it and be able to find other Earths around other suns with this method. Now, there's a lot of different detection methods, and I'm not going to go into every single one, although if you have a question about any specific one, I'm happy to answer it. Anyways, in these first dozen or so years of exoplanet hunting, this is a plot of planetary mass versus orbital period on the x-axis. The orbital period is how long it takes for a planet to orbit around its star. And you'll see that most planets are really, really massive. They're more massive than Neptune. About 85% of the planets on this plot are more massive than Neptune, and actually a lot of them are more massive than Jupiter. And you'll also see that these early exoplanet detections had a lot of giant-sized exoplanets, like Jupiter mass planets that have very, very short orbital periods of only a few days. So these are called hot Jupiters because you have these giant planets in very close in and therefore very hot orbits because they're so close to their stars. And the discovery of hot Jupiters, which were a large component of these early exoplanet discoveries, caused us to rewrite a lot of our planet formation theories. Because if you look at our solar system, we have the small terrestrial planets close in, and we have the large gas giants and ice giants far away. And so we thought, well, planet formation, can only form these really big planets far from their stars for various reasons. And then we found these hot Jupiters, and that's just completely contrary to what we see. And it's actually still an open question today, how we have hot Jupiters in their current locations. So this is still a really open question in astronomy. But you'll see that there aren't any small Earth mass exoplanets. And I know that the plot legend here is kind of covering up that parameter space, but trust me when I say that there are no planets in this low mass regime. And it's not that planets here don't exist or are not common. In fact, we know we exist, and now that we have many more years of exoplanet discoveries, we actually know that they are very common. But at the time, these first 20 years of exoplanet discoveries, we didn't have any. And that's just because we didn't have the technology and the sensitivities to be able to find them. But that changed with NASA's Kepler mission. So Kepler was NASA's first ever exoplanet finding mission. It launched in 2009, and it had the specific goal to find other Earths around other suns. So these are Earth-sized planets in year-long orbits around sun-like stars. And the way that it did that was using the transit method. This is the last method I'm going to talk about, and it's also the method that I use in my research primarily. Now, the way that this method works is we have a planet in orbit around a star. And if that planet happens to pass directly between us and the star, it will block a little bit of that star's light. So if we're measuring the brightness of that star over time, we'll be able to see a temporary decrease in the measured brightness. And this is what we call a transit. Now, because the planet is going to complete an orbit once every orbital period, the time between these transits tells us how long it takes for that planet to orbit. And the overall decrease in brightness, the transit depth, also gives us a sense of how big the planet is. A big planet is going to block a lot of light, and so it's going to cause a large decrease in brightness when it's blocking light. And a small planet is going to block only a small amount of light, so it'll have a much shallower transit depth. But planets are really small compared to their stars. The Earth, for instance, is hundreds of times smaller than our sun. And so it only blocks 0.008% of the sun's light. So if we want to find other Earths, potentially habitable planets, we would need to be able to see such a small change in brightness. And there's a really useful analogy that I like to use that helps you picture what I mean by a 0.008% change in brightness. So I want you to imagine the Empire State Building, and let's say that it's nighttime, all of the lights are on, and all the window shades are up. And for context, I think the Empire State Building has about 6,500 windows. Now you can imagine that somebody is standing next to a window shade, and they pull down the window shade by just a few centimeters. And you have to detect the change of brightness from that motion from 100 kilometers away. And now consider that a transit is only going to last for a few hours. And if you're looking for another Earth, which takes a whole year to travel around its star, this is going to happen only once a year. So you need to be staring at the same star for years on end, continuously measuring the brightness of that star, like multiple times an hour, just to be able to see a few transits. And that's exactly what Kepler did. So Kepler looked at about 150,000 stars between 2009 and 2013. And it had a very, very large field of view. So 115 degrees squared is about the size of the night sky if you were to hold your hand out at arm's length. That's about how much of the sky that it was looking at. At the time, that's a relatively large field of view for a telescope in space. It was at the time the largest mirror ever sent into space with a diameter of over 1 meter. And it was also at the time the largest camera system into space. So for many reasons, it was quite revolutionary. And it was launched into an Earth trailing orbit, which means it kind of follows the Earth as it orbits around the sun. And you can see here that it has these blue solar panels, and they're always pointed at the sun so that it has power from our sun. And so you can see that it rotates on its axis every quarter of a year. And that's just so that those solar panels can always be pointed at the sun for power, but the telescope itself is always pointed in the same section of the sky, so we can get those continuous monitorings of stellar brightness. So it looked at those 150,000 stars for 4 years, recording a measurement of every single one of those stars' brightness every 30 minutes. And to give you a sense of just how successful Kepler was, here's a plot of the number of new planets discovered per year, starting with those early detections in the early 90s. And the blue parts correspond to non-Kepler detections, and the red parts correspond to Kepler detections. And you can see that in the first few years of the mission, Kepler was pretty successful. It was finding a lot of planets, especially compared to the combined efforts of every other survey telescope method that was trying to find them. And after they completed their 4-year mission, they started to release more data releases and catalogs now that they had all this data. And they kind of blew everybody out of the water with their 2014 catalog. They found over 1,000 planets alone in that one catalog, and that was just the first of many. They have since gone on to find about 4,700 planets and planet candidates. And this is just another view of that. This is the plot I showed you before of planet mass versus orbital period before Kepler, so in the first 20 years of exoplanet discoveries. And this is the plot after Kepler. Now I'm showing planet radius versus orbital period. And so you can see that Kepler finally filled in that incredible small planet parameter space, including smaller planets that are smaller than the Earth, for really the first time. So for the 4-year mission, it found 2,700 confirmed planets and another 2,000, which we have not yet confirmed as planets, but we nevertheless believe are very likely to be planets. And unfortunately, it did end its mission early. It could have observed the night sky for a lot longer, many years longer, which would have been amazing. But it did have some instrumental failure, and it had to shut down in 2013. It ended the mission in 2013, and the telescope itself was shut down just a few years ago. Just a side fun fact, when Kepler was shut down in November a couple of years ago, the very date that it was shut down was one day off the anniversary of Johannes Kepler's death. Johannes Kepler was the namesake for the telescope. So it's kind of poetic in that way. But moving on, now that we are in the era of TESS, TESS is NASA's Transiting Exoplanet Survey Satellite. And kind of like Kepler, it's using the transit method to find exoplanets. But unlike Kepler, which looked at the same section of the sky for 4 years consecutively, it's looking at the entire sky. It's looking at basically every nearby and bright star to try to find exoplanets. And so what it does is it looks at these huge strips of the sky called sectors, which have an enormous field of view, many, many times larger than Kepler. And it looks at every star that's in these sectors, millions of stars, for 27 days, and then rotates to look at the next sector of the sky. And once you've gone around 13 sectors, 13 27-day chunks, you've roughly been observing for a year, and that's enough to cover an entire hemisphere of the night sky. So TESS basically looked at the southern hemisphere for 1 year and then flipped over to look at the northern hemisphere for another year. And we're now 6 years into the mission, so it's been looking at the same sections of the sky, it's been revisiting different areas, it's been filling in some of the gaps that were left behind in order to fully map the sky. And I think at this point, it's mapped out over 96% of the sky. And because it's an all-sky survey, it's giving us a much better sense of how exoplanets are distributed around our local sky. So here's a plot of all of the planet discoveries, including planets and planet candidates that were found before TESS. And you can see at the very top, there's that really big concentrated bulge, which is the Kepler discoveries. So there's 4,700 planets and planet candidates, all concentrated in that one collection. And you can see that there's different scatters of other exoplanets found by other techniques and other missions. TESS, however, has been finding many, many more planets all around the sky. It's now at almost 6,000 planets and planet candidates. And because it's continuing to observe, hopefully, it continues to get funding from NASA to be able to keep taking more data. And there are simulations that have predicted that TESS should find over 10,000 planets within the next few years. And when I worked on the TESS mission, I both led MIT's Planet Search Pipeline, which was part of the TESS Science Office, but I also ran an independent planet search pipeline using my own tools, which is known as the TESS Faint Star Search. And the TESS Faint Star Search actually found about 45% of all of these planet candidates. And it's something that I continue to do at UBC. Maybe every month I find several dozens of new planets for TESS. So what does that actually look like? Well, TESS is taking the data from stars every month, every 27 days, and it looks kind of like this. We have a measurement of the brightness over time. And what I do is I run an automated planet search algorithm on this light curve to be able to say whether something is transiting. And in this case, my automated search algorithm would have picked out these two dips here, because you can kind of see that they're similar in depth. And if you were to zoom in on them, you'd also see that they are similar in duration. And then the next step is to say, well, I found something that looks like it's repeating, and it looks like these are consistent transits with the same depth and duration. So is this caused by a planet, or could it be something else? Because there are other things that can mimic a planet in the data. For example, maybe I didn't see a planet transiting the star and blocking its light, but it's a brown dwarf or another star that's passing in front of our target and causing its brightness to be decreased. So there's always this question of, how can we best classify the signals that we're detecting? Many people use machine learning to do this. There's other techniques we can use to do this well, but it's a very important step to, always be investigating alternative explanations for the types of signals that we're finding. And now that we've reached the present day, with TESS currently observing Kepler data having been completely released, and people, even are still using Kepler data to find planets, we know of about 5,800 total confirmed exoplanets, over 4,000 of which were from the transit method. And this number doesn't include the several thousands of candidate planets that haven't yet been confirmed, but have been found by TESS and Kepler and other missions. So overall, I would say that we probably know of more than 10,000 planets. We just haven't confirmed them all yet. Now here's a plot, kind of an updated plot of the masses of different planets versus their orbital distance. So how far away they orbit on average from the star. And I've color-coded them by different detection methods. So you can see those light blue points on the left are those from the transit method, and the yellow ones are from the radial velocity method, and there's some other methods that I haven't covered that are finding planets in different areas of parameter space. And we can already start to see that there are these different trends in the data, different classes of planets that seem to be popping out. So the first two I want to mention are the Jupiters. There's the hot Jupiters, which are very, very short orbital distances. And then there's the cold Jupiters, which are kind of like Jupiter in our own solar system. We've also found a lot of examples of rocky worlds that are in those really, really close in distances. And I've also shown on this plot the locations of the planets in our solar system. And you can actually see that Mercury is our innermost planet in the solar system, but most of the planets we found with the transit method orbit far within it. And so you have these rocky planets that are really, really close to their stars, and they're very hot. And what happens when you take rock and you heat it to high temperatures? You get lava. So these are also called lava worlds. And the most common size of planets we found so far are those between the sizes of the Earth and Neptune. So planets that are a little bit larger than the Earth, we call super Earths, and planets a little bit smaller than Neptune, we call sub-Neptunes. And these are very interesting discoveries because they're the most common planets we've found so far, and yet there isn't a planet of this size in our solar system. So it's actually an open question why our solar system doesn't have a planet of this size, despite them being apparently really, really common. We've also found planets that don't orbit one star, but they orbit multiple stars in binary star systems, even 3 stars or 4 stars or more. And these are kind of like, Tatooine in Star Wars, that's a binary star system. We've also found planets or planetary mass objects that don't orbit any star at all. So we call these rogue worlds. Maybe they originally were part of a system very much like our own, but some event caused them to be ejected from their systems. And so they are now freely floating throughout the galaxy, not bound to any particular star at all. So we found a lot of planets so far. As I mentioned, we've got over almost 6,000, many more thousands of candidates. How many of those might be considered potentially Earth-like? So we can really start to dive into, have we found any planets that are potentially habitable? How common are planets that look like our Earth? So I'm going to go over some very basic definition of what I mean by an Earth-like planet. And I do want to emphasize that I'm going to use a very Earth-centric definition because we know of only one planet that hosts life, which is ours. And so, we basically have one data point that we're extrapolating from, and you should never extrapolate from a single data point. So for example, we're going to assume that life needs water to survive, and that's because life on Earth needs water to survive. But there are other explorations in the field of astrobiology to kind of challenge that notion and say that we might be able to have life that doesn't look like life on Earth. But with that caveat aside, what are the basic criteria that we use to define an Earth-like or potentially habitable planet? So the first criteria is, what is the size of the planet? If it's roughly 0.5 to 1.5 times the size of the Earth, we say that it's roughly Earth size. And the reason this is important is because the size of the planet is closely tied to its composition. And once you get to these really, really large planets, they tend to be gaseous. And once you get to these really, really small planets, smaller than half the size of the Earth, you have planets that have very low masses, and that means that they don't have a high enough mass to hold on to a thick atmosphere. So Mars is an example of a planet with a very low mass that does have an atmosphere, but it's very thin because the mass is just not strong enough to sustain a thick atmosphere. And our atmosphere protects a lot of life on Earth, and so we really want to make sure that if we're looking for potentially habitable planets, that they can have a nice atmosphere that will protect the life. Secondly, we're looking for planets that are in their habitable zones. So this is a range of distances from a star where a planet can support liquid water on its rocky surface. If a planet is too close to the star, it's going to be too hot, and liquid water is going to boil away. And if it's too far from the star, it's going to be too cold, and liquid water is really only going to be able to exist in the form of ice instead of as a liquid. But specifically, what we need is liquid water to survive, and so we're looking for planets that are not too hot, not too cold, just the right temperature to support that. And finally, we're looking at the type of star that planet orbits around. One of the reasons this is so important is because we believe life needs billions of years to survive. And if that sun that the planet is orbiting around only lives for less than 1 billion years until it, explodes into something and ends its lifetime, then that's not going to be really great for the development of life on that planet's surface. So planets or stars that are much larger, hotter, more massive than our sun go through their fuel a lot faster, and so they die quickly. They will end their lifetimes, at a much shorter time scale compared to our sun. So it's not good to look for habitable planets around these really, really big stars. On the other hand, stars that are much cooler and smaller than our sun, known as red dwarfs, do actually live a really long time because they don't go through their fuel very quickly at all. They'll actually live a lot longer than our sun. So they could be really good places to look for Earth-like planets around. They're also about 70% of all stars in our galaxy. So if they can support planets that have life on their surfaces, they could be the most common planet hosts. There are a few things I want to mention that are not good things about these types of stars for habitability. One is that because these are so cool, their habitable zones are much closer in. Kind of think of it like you have a fireplace going and you're huddled around the fire. If the fire is a lot smaller, it's not producing as much heat, you have to huddle closer into that star. So what happens is when you're huddled in really close, planets tend to be tidally locked, which means that the same side of the planet is always facing the star. And so you'll have perpetual day side on one end and perpetual night side on the other. And it's not clear how that affects habitability. Also, because you're so close to the star, you're bombarded by a lot more direct radiation. And so it's also not clear how that will affect the development of life on that planet's surface. Not to say that more radiation means that it's impossible, but it is something that we have to consider. If we were to find a planet that is the size of the Earth and in the right habitable zone around a sun-like star, then that is, of course, an ideal discovery because it's closest in conditions to what we are experiencing on Earth. So far we have found several dozens of planets that fit these basic criteria, most of which are around those really common low-mass stars. And based off of how many we've found so far, we can extrapolate and actually say that about half of all sun-like stars host a planet that is similar in size in the habitable zone and orbiting a sun-like star. And since there are several hundreds of billions of sun-like stars in our Milky Way galaxy, that means that there are several hundreds of billions of potential other Earths, which I think is really cool when you dive into the statistics of it, because that makes me think that life has to be out there. And in fact, the very closest system to our Earth, Proxima Centauri, this is the closest star, it hosts a planet that is rocky in the habitable zone of its star, it's Earth size, and it's the closest planet to our solar system. And I think this is one of the reasons why it's one of my favorite planets, because the very fact that the closest planet to our own solar system is in the habitable zone and potentially habitable makes me think that there must be our universe must be teeming with them. In terms of the planet that is most like the Earth, we found Kepler 452b. This planet orbits a star that's about 10% larger than the Sun, but it's the same type of star. Its orbital period is 385 days, so it takes only a little bit longer compared to the Earth to orbit. And it's only 10% of the size, 10% larger than our Earth. And so it's definitely in that rocky regime. And so of all the planets we've found so far, these are the one that's got its physical properties and orbital properties that are closest to the Earth. Another system I want to mention, which was found a little bit more recently and has attracted a lot of attention, is the TRAPPIST-1 system. So this is a system of 6 rocky exoplanets, and no, 7 rocky exoplanets, sorry, I misread that. And what's really cool is that they're all roughly Earth size, and 3 of them are in the habitable zone of that star. So it's not just 1 planet, it's not 2 planets. 3 of them are all rocky exoplanets in the habitable zone. And because this TRAPPIST-1, the star itself is really, really, really low mass. It's really cold compared to our sun. These planets are really, really close in. And actually, if you were to take the TRAPPIST-1 system and place it in our solar system, you can see in the bottom picture here, all of those 7 planets would be orbiting within the orbit of Mercury. So it's a really unique system, and because it's got all these planets in the habitable zone, it's actively undergoing follow-up that is trying to see if we can detect different things in those planet atmospheres, which I'm going to get to in a little bit. So speaking of, let's say we found planets that fit all of our criteria for what is considered an Earth-like planet. It is in the habitable zone, it has the right size for a rocky exoplanet that can sustain an atmosphere, and it orbits the right type of star. How do we actually tell if there is life on that planet's surface, or what can we do to better understand the potential for habitability for that specific planet? So there's a few things that we can do now. The first one is better understand the actual composition of the planet itself, because the transit method, as we've already covered, can tell us something about the size of the planet, the radius of the planet, but it can't tell us anything about the mass of the planet. The radial velocity method, meanwhile, is dependent on seeing something like the gravitational influence of that planet on the star, which is why it tugs on its star and causes it to wobble around the center of mass. So it can tell us something about the mass of the planet, but not the size. And so you can combine these two, the mass from radial velocities and the radius from the transit method, to estimate planet density. And density is a really important tracer for planet composition and internal structure. So given the density of a planet, we can guess what material is mostly, the planet is mostly composed of. We can actually say whether it's got a density like the Earth, if it has a density like our gas giants, or if it's somewhere in between and could potentially be a planet that's covered in water, like a water world. But we can also actually tell the composition of another planet's atmosphere. And there's this really cool technique that is the most popular to do this, known as transmission spectroscopy. Now, the idea behind this method is it uses the transit method to characterize atmospheres. Because planets have opaque rocky cores and they have an atmosphere around them. And when that planet is passing in front of your star and blocking its light, the light from the star itself, of course, is going to be blocked by the rocky part in the center of the planet, and it's also going to pass through the atmosphere because it's not opaque. But at some wavelengths, there could be a molecule in that planet's atmosphere that is absorbing light from the sun. Just like how we saw those black lines in the star spectrum, those were absorption features caused by some molecule absorbing light at that wavelength. And it's the same thing here. So if there is some wavelength where light is being absorbed, then less light is going to be reaching our observers. We're going to see a larger transit depth because more light or less light is arriving. And so by simply looking at how deep a transit is at different wavelengths, we can tell that there's some molecule in that planet's atmosphere that's causing the change in transit depth. Now, specifically, what we can do is look for features caused by biosignature gases, which could indicate the presence of life on another planet. Now, biosignature gases are gases that are produced by life. They can also be produced by non-life, but they are examples of things that can be produced by life or could otherwise indicate biological processes. So examples could be water, carbon dioxide, methane, Oxygen is another one, ammonia. So there's possibly, the detection of water in another planet's atmosphere is not enough to say that water is therefore on the surface and life is there. But maybe there's some combination of these biosignature gases that can only be explained by some biological process. And this is one of the ways that we can start to understand the conditions on the planet's surface and the likelihood that life could be producing these gases in the planet's atmosphere. So just as an example of a real life application of this technique to understand the potential for another planet in terms of its habitability, last year there was a discovery of methane and carbon dioxide in the atmosphere of K2-18b. Now, K2-18b isn't a small rocky terrestrial planet like the Earth. It's several times larger, but its density is consistent with it being an ocean world. So it's got a rocky core, but it's covered in a thick layer of water based off of our understanding of its density and its other properties. And so already discovering these biosignature gases is pretty cool, but of course we can't know if those alone can be, only explained by life. But there was also the detection of something, or a possible detection of something called dimethyl sulfide, or DMS, in that planet's atmosphere. And on Earth, DMS is only produced by life, other than in very, very, synthesized lab environments. You can really only produce DMS by phytoplankton in the Earth's oceans. And so this is potentially a ocean-covered planet. And if this detection of DMS is real, the story does line up. The observers did want to emphasize, though, that this detection was very weak. It could be explained by something else. It's not clear yet if this was actually DMS, but it's a pretty a promising line of inquiry that we can better understand. And so what they planned to do is take more observations with James Webb to see if that DMS detection would get stronger, or if it would get removed, or if we can start to pick apart, and try to understand what features are actually in this planet's atmosphere. But nevertheless, I think it's a really exciting discovery, even if it's tentative at this stage, because it's a demonstration of what we can do now to start looking for life on another planet. So before I close up here, I want to just let you know that all of the planet discoveries with the transit method, like using the light curves and looking for planet transits, is a way that you can also get started with hunting for exoplanets. And this was a technique that I used as an undergraduate student just a couple years after I was in Science 113 to find my own planets that no one had ever found before. And one of the reasons this is possible is that a lot of the data is available. And I had taken this course called Exoplanets and Astrobiology, which is taught here at UBC. It's Astronomy 333. And this was actually the first time I'd ever learned about the transit method and the radial velocity method and pulsar timing and all the other detection methods. And it's also about habitability criteria and how we can search for life on another planet's surface. And when I took that, I was really, really inspired to try to understand, if there was a way I could get involved as an undergraduate researcher who had no research experience at the time. And I was assigned kind of a project to take data that was publicly available from NASA's Kepler mission and to try to see if I could find any new planets. And so you can actually download all of Kepler's data and TESS's ongoing data from the Mikulski Archive for Space Telescopes. And there's also a lot of online resources to help you get started with using Planet Search code bases and to run this. And so that's really what I did as an undergrad. I had no research experience, but I was given, a lot of light curves. And then I just looked online for some helpful tutorials and people who had already written code to do this. And what ended up happening was the discovery of 4 new planet candidates. None of them are small rocky Earth planets in the habitable zone, but that really big one on the right, KOI 408.05, was actually independently discovered by another group trying to do the same thing while I was working on my project, and they found the same planet. So that is a good indication that it is actually a real signal. And it's a Neptune-sized planet in the habitable zone of its star. So maybe the planet itself is not rocky, but if it has a moon in orbit around that planet, maybe the moon is small and rocky and could be in the habitable zone. Just like in the movie Avatar, the planet that they're on is actually a moon around a Saturn-sized exoplanet. So maybe I found Pandora. But for those of you who, don't want to be going and downloading code bases and using a lot of programming knowledge, there's also a really great way to get involved with planet hunting using just your own eyes. So there's this website called Planet Hunters Tests, which hosts data from the test mission. And you can just look at the light curves themselves and see if by eye you can actually detect an exoplanet. And this is a really great way to find exoplanets because we have a remarkable ability for pattern recognition. In many ways, we actually do a better job than our automated algorithms do. The benefit of the automated algorithms is just that they can run a lot faster, and it's infeasible for us to look at millions of stars. But people have actually used Planet Hunters tests just by eye identifying possible planets, and they have found hundreds of planet candidates that were missed by professional teams around the world. And in fact, some of their discoveries have been particularly, unique and strange because they are not exactly what automated algorithms are necessarily designed to find. And so Planet Hunters is a great way for you to get involved in planet hunting. And again, it just requires your internet browser and an understanding of, what a transit looks like, so you know what to look for. So I'd really recommend, you can get involved with that. So last thoughts, exoplanet hunting has really exploded in the last few decades, and it shows no signs of stopping. It's one of the fastest growing fields in astronomy, having gone from just a few detections in the 90s, a couple dozen by the year 2000, a few hundred by the year 2010, and now we are at thousands and thousands of exoplanets. It's really exciting to be a part of. And the future of exoplanet hunting is also really bright. The Plato mission is going to launch in a couple years. This is a European Space Agency mission designed to find transiting planets. And there's also NASA's next flagship mission called the Nancy Grace Roman Telescope, which will launch around the same time. And it's also going to use the transit method, as well as another method called microlensing to find new planets. And they predict that they'll be able to find hundreds of thousands of new exoplanets. And there was actually a huge survey that's done every 10 years. It's called the Decadal Survey. That's basically asking astronomers around the world to provide input for what should be the priority in astronomy in the coming decades. And for the Astro 2020 Decadal Survey, astronomers highlighted the search for habitable worlds should be the top priority. And as a result, NASA selected the Habitable Worlds Observatory as its future flagship mission. So following the Hubble telescope, the James Webb telescope, the Roman telescope, Habitable Worlds Observatory should launch in the 2040s. And its goal will be to directly image other Earths and search for biosignature gases in those planet atmospheres. So that means not just indirectly finding planets by their transits or the radial velocity motion of their stars, but literally directly taking a picture of another Earth around another a sun-like star and seeing if we can characterize its atmosphere. So this is going to be the first time it'll be possible with the direct imaging method, and it'll be really, really exciting to be part of. And as we find more and more planets, our perspective of planets in the Milky Way is constantly changing. We found so many examples of hot Jupiters, which caused us to rewrite our planet formation theories and is still an open question about how they can exist in the current orbits. And we've, of course, found so many examples, dozens now, of potentially habitable planets in the habitable zone that are the right size. And the more of these we find, we can start to understand just how common life on our little planet actually is. And one of my favorite things about exoplanet astronomy is that anybody can take part. I took part as an undergraduate. People have found their own planets as high school students. It's really accessible and it's really cool to be part of scientific discovery. Before you get your PhD, you can still contribute to astronomy and make some really cool discoveries. And I would love to answer any questions about how to get involved because I will also be looking for students that can help me with finding their own planets. With that, I will take questions.
Amazing. Thank you very much, Dr. Kunimoto, for an excellent seminar and lecture about all your exciting exoplanet discoveries and all the different methods used to be on the hunt for exoplanets. So we do have some time for questions, and so we definitely invite you to write those questions pertaining to Michelle's talk in the chat, and we can also take questions by folks raising their hands, which I see a few of you have done. So, Celine, why don't you kick us off?
Hello, Doctor. Thank you so much for your wonderful presentation today, and thank you so much for your time. Can I just ask quickly, originally, what was your actual research question that you were asking yourself while you were actually trying to detect these exoplanets? Did you have like a question in mind, or was this just maybe a project that you were doing out of interest?
Yeah, so I think the guiding question for me was to search for another planet like our Earth, specifically so one that's Earth size and has a year-long orbit. And because these are at the limit of our detectability, like they're really small, so they have such small transits, they're really hard to find. And so by looking through the Kepler data set, I was thinking of the planets that would have been missed by previous efforts to look through here, it would be the really small, potentially Earth-like planets that are the most easy to miss. And so a lot of what I did specifically as an undergrad was take established algorithms to look for planets, and I tried to improve them for very, very low SNR or low signal to noise ratio signals. Like an analogy that I could use is like imagining that you're in a crowded room and you're hearing a lot of people try to talk to you. And a lot of previous detection pipelines had focused on only trying to hear people talking really, really loudly above the noise level of the room. But the work that I tried to do was spend extra time trying to listen to people speaking really quietly compared to the noise level. And those were the types of signals that I was trying to find with the intention of hopefully finding some that are potentially habitable. So none of the planets that I found in my undergraduate project ended up having those criteria because they were really hard. But as a PhD student, I extended that search to many more stars, and I did find one planet candidate that was roughly Earth size in the habitable zone. So that was kind of a ideal outcome, I guess, of my research. And then as I extended that to the TESS mission, it's become not just about Earths, it's been about a lot of really unique planets that are in different areas of parameter space.
Thank you for your answer. Do you mind if I just ask you another quick question? Um, how did you get your scientific discoveries recognized? Like, what steps did you actually take after your discoveries to present it to the scientific community?
Yeah, so I wrote a paper as an undergraduate. So this was a peer-reviewed journal article that I was the lead author for, where I described the steps that I took to find those planet candidates, what data set I used, what algorithms I used, how it was different compared to what other people have done. And part of the recognition process is the reviewer, agreeing with your conclusions, reviewing your work through peer review, and having that paper be published. And that was kind of the major way that I've done that for my undergraduate work. As a postdoc at the TESS mission, because I was literally within the TESS science office, I had a lot of control over what signals get recognized as official planet candidates from TESS. And so I helped manage the TOI TESS Object of Interest catalog. So the recognition came mostly through my role as the TESS Object of Interest manager.
Thank you so much for answering my questions.
Thanks for the questions.
Yeah, thanks, Celine. That was a great follow-up. Let's go to Sierra next.
Hi, thank you so much. I had a question about I guess it was maybe sort of answered in the question just before, but do you have like a favorite planet that you discovered or that like maybe a peer discovered, something like that?
Yeah, that's a really good question. Because I think, over 3,000 by now. It's hard to pick a favorite. So I think one of my favorites was one I found a couple years ago. And the reason it's a favorite is because it's in a really, really rare parameter space. Actually, if we go back to the pictures I showed about the planet population, you can see that there are areas where there's a lot of planets and areas where there's no planets or very few planets. And part of this is just due to bias. Some planets are more easy to find than others, and so they're going to be overrepresented in this plot. But some of these areas of few planets are because of some physical reason. And one of the most important ones is this one here. There's no planets you see here. You see large planets, you see small planets, but nothing of intermediate mass or intermediate radius. And one of the planets I found is right in this region. And so it's really cool to find a really rare type of planet. And I was able to get time on the James Webb Space Telescope to actually characterize this planet's atmosphere and help us understand why it's so rare. And so James Webb is actually going to be looking at my planet in a couple months. And so that'll be the first time I've had my planet looked at by this, multi-billion-dollar telescope where 1 hour is millions of dollars, it feels like. So I think, yeah, that's a cool planet that I found. It has very rare properties.
It's very, very cool. Thank you so much. Is there a way that we'd be able to like read online, I guess, after you're able to do that viewing on the telescope to kind of see what's discovered, or is that not going to be accessible to other students?
Well, I do have a research website. So if you just Google my name, you should see like there's a GitHub website, and I talk about this particular planet on that website. So you can read the discovery paper. The James Webb observations are not going to be released to the public until I've had a chance to like go through the data myself, because James Webb gives like the people who proposed for time a proprietary period, which means you're the only one who has access to this. And it's there to help make sure that someone else doesn't take your data that you've asked for and proposed for and scoop you in doing science with it. So I think the proprietary period is like a year, and I'll be able to release the results of that work, over the course of after that period when I've had some time to analyze it.
Thank you so much. I hope that I'm able to read that someday. That'll be very cool to see. Thank you.
Yeah. Thanks.
Thanks, Sierra. I'm going to switch and just ask a question from the chat, and then we'll come back to the folks with their hands raised. So I'm not sure, Michelle, if you can see the chat, but I can read out the questions.
Sure.
We've got a question from Bella who's asking if there are 3 potentially habitable planets in the TRAPPIST-1 system, and the whole system is sort of close enough together to fit within Mercury's orbit, how easy or difficult would it be to travel between them?
Oh, that's a great question. Well, I think it would be definitely a lot easier than it is for us to be traveling between our solar system planets and within our solar system. And actually, if you look here, for instance, at just the orbital distance, some of these planets are really, really far apart. Whereas I think that the TRAPPIST ones are all just kind of clustered down here. So it would be, if there was like some civilization on one of those planets, I think it would be relatively easy for them once they got space travel, just like how we've been able to reach Mars, to be able to travel to some of those neighboring planets.
Yeah, it's a great question.
That's a great question for a science fiction novel.
Yeah, that's true. Okay, we'll go back to the folks with their hands raised, and I apologize if I don't pronounce names right, but we're going to go to Tylee.
Yeah, Tyler.
Tyler, yeah, go ahead.
Okay, thank you, Doctor, for your presentation. I have 2 questions. My first question is, what do you think in astronomy, like when you look at universe or galaxy, like is the more we find out or the more we discover, is there more unknown, or do you think we are actually knowing more, reducing the unknown?
I think that it's both, because the more we know, the more we realize we don't know. I mean, actually just looking at this plot here is a good representation of that, because yes, we found so many planets at the transit method and we start to really understand planet diversity, but then we realize that there's this enormous empty region, the bottom right corner, where we just don't have any planets. And I think when we look at this, we think, wow, we actually have not really been able to find planets across all areas of parameter space. There's so much more that we don't understand. And the more planets that we find that don't meet our expectations for, how the solar system formed, for instance, they open up new questions that help us start thinking about new lines of inquiry and new theories to explain things, and being able to develop different models that can explain all the observations we have right now. And because we're constantly discovering new planets, we're constantly changing our models and seeing, you know, where they are lacking in some areas. And yeah, so it's like, obviously the more data that we have, the more planets we have, we're learning more and more, but we're also having we're better informed to ask questions that we wouldn't have thought of before.
Yeah, it's a really great question. Yeah, it kind of gets into the philosophy of, yeah, science in general. It's wonderful. I'm going to go to the chat. Chris has a great question about naming planets. How do you go about naming the planets you found, and is it under your control?
Generally, it's not under your control, unfortunately. It'd be really cool if I could give my planets really cool names, but they're given a very technical name that is after the star that they were orbiting around. So as an example, the planets that I found with the TESS mission all are TOI, test object of interest, and then the number, a number that corresponds to, chronologically speaking, which planet, like what number of planet is this? So the very first test planets were TOI 100. I don't know why they started at 100 instead of 0, but that's just how it is. And so TOI 4000 is the 4000th planet that they found. TOI 5000 is the 5000 planet they found, the host, and then the planets that orbit around that star are 0.01, 0.02. So as an example, the first planet found around TOI 5000 is going to be called TOI 5000.01, and the second planet will be 0.02, and so on. So it's all this very technical tracking so that we name our planets after the star they were orbiting around, and then they're numbered or lettered by what order the planets themselves were found. There are some planets that have special status, and they do actually have official names as recognized by the International Astronomical Union that are, really unique. This is something that's controlled by the International Astronomical Union. Not every planet gets this kind of special naming.
Great question. Let's go to Ahmed. Go ahead.
Yeah, hi, Doctor. I really appreciate your time, and it was a great presentation. I just wanted to know a little bit more about how you use machine learning in some of your research. I thought you mentioned machine learning, and wanted to learn more.
Yeah, so machine learning is one of the ways that it's useful is as a classifier. Like, let's say we have a whole pile of different signals that are possibly caused by planets, but there's other things that they could be explained by. So planets are one scenario, stars are another scenario, just simply random fluctuations in the data is another scenario. There's different explanations for what we're seeing in the data. And so machine learning can be used to take a signal, take the measurements of brightness over time, and classify it into those various categories. And then as we're putting together our planet catalogs, we're basically looking at things that pass with a certain strength, that it's sufficiently consistent with the planet, as determined by some algorithm. So machine learning is an example of a way to do that. There are other ways to do that without machine learning, but machine learning is really popular right now to do this classification of different signals.
I appreciate it. Thank you so much.
So in the chat, Denise has a good question. Is it possible for us to travel or land something on the planets in the habitable zones to observe the planet's environment more closely to confirm their habitability?
For exoplanets, we're limited by how difficult it would be to reach another planet, even just sending a probe. So currently, we don't have the resources to be able to do that for an exoplanet. But if we did, then that would be a really great way to better learn about the planet's surface. Like, we could send a probe and take pictures and, even, monitor things like the temperature, see how it changes over the course of a day. But just as an example of something that we can do with our solar system, there is actually a mission, there are missions that are designed to better understand moons in our solar system, because there's one, for instance, called Europa, which is one of Jupiter's moons, and it has potentially a thick layer of ice over a thick layer of liquid water, like an ocean. And so one of the possible, future missions could be to send a probe to Europa, because it's within our solar system, it's within our capabilities now to, see if we can actually understand the composition of the water underneath the ice. So there's definitely ways that we can better understand, just beyond looking at a planet's atmosphere and its basic properties. But for exoplanets, it's currently out of technology, but in the future, it will hopefully be possible.
Great, thanks. Let's go to Janelle.
Hi, doctor. Thank you so much for your time. So I just wanted to ask, like, with the many exoplanets that we've discovered in only 20 years, like, with your knowledge and experience in the field, like, what would you think are the possibilities of us actually discovering, like a habitable planet? And, like, how would we actually confirm it, especially with a lot of them being so far away? And you mentioned it in your presentation, like, use, like, the unconfirmed planets. So what would actually, like, confirm the planets?
Yeah, so basically, I kind of touched on there being other explanations for the signals that we find. So like it could be that a star is causing the signal that we think we see from a planet. It could be random noise, it could be something else. And so the confirmation process usually involves doing follow-up from other telescopes and other methods that can remove those possible scenarios as explanations. And once we've removed enough of them, or we've been able to see the same planet with multiple detection methods, like both transit and radial velocity, both see the same planet with the same orbital period, and everything looks right, then we can say it's confirmed. So the planet candidates are basically at a stage where we found them with the transit method, but we don't yet have a detection with the radial velocity method, or we don't have enough follow-up observations from other telescopes to remove false positive scenarios enough to say that it's not one of those, that the only explanation that remains is a planet. So the confirmation process is long. There are hundreds of planets currently undergoing follow-up as we speak. I think we won't be able to get through all 6,000 test planet candidates anytime soon. So we prioritize some, like if it's in the habitable zone, it'll be a higher priority. And one of the reasons why TESS was designed to look for nearby bright stars is because bright stars are a lot easier to follow up. So we have much better prospects for actually confirming potentially habitable planets found by TESS than those that were found by Kepler, which looked at very faint stars. So there's a lot of moving parts, basically just performing follow-up observations to better understand possible scenarios that could explain the signal, better understanding the properties of that planet, and doing the kind of the ultimate goal right now, which is atmospheric characterization to see if we find biosignature gases.
That's really interesting. Thank you so much. And I have just one more question. So like when you're trying like to get your research across to others, what would be like the biggest kind of main claim that you'd like others to understand, especially with like this kind of, research about like planets and stuff?
Biggest claim, I think I find the kind of the statistics about the commonality or the abundance of potentially habitable Earth-like planets is really mind-blowing. Like people, when you start to break it apart, you say, well, if they're, around 50% of all sun-like stars, and there's hundreds of billions of sun-like stars, just do the math, that's how many possible Earths there are in the galaxy. And I think that when people hear that number, they think, oh, life feels like it should be really common in that case. There is a large uncertainty in that number of 50% I just mentioned. And that's actually a big open, like a big active field of astronomy, is to try to reduce that uncertainty and better understand what exactly it means for a planet to be potentially habitable, Earth size. What does sun-like star even mean? But I think like just demonstrating that we found a lot of really exciting planets, including those that are potentially habitable, and our numbers currently point to them being really, really common, is a really big takeaway that I hope people leave this talk with.
Thank you so much. I really appreciate you answering my questions. Your research is so interesting.
Thank you.
Well, in our last couple of minutes, I apologize, we might not get to everyone's question. I will just go to the chat for a moment and just ask Yasoda's part of your question there in the chat is just the types of, there's all these different methods that you talked about. Was the transit method your preferred or favorite method, or did you use the other ones? Or like, how do you choose maybe which method you use?
So primarily I use the transit method, and the reason is just because it's the most popular. It's the most, like, the more data is available. Like, all of Kepler data is just available. All of the test data is available to the public within a few days of tests actually taking the observations. Like, there's no waiting period between when the public gets the data and when the science team gets the data. And so it's really accessible. Like, anybody can run their own planet search with transit data. The other methods, like radial velocity, different teams tend to be more protective of their observations, and it's like you need to be on a telescope team that does this type of work in order to gain access to that data and use it to do planet discoveries. And so it's not as accessible for someone who isn't already in one of those collaborations. I do use the radial velocity method to confirm planets that I find with the transit method. So that would be like, I find a planet with the test mission, and then I write an observing proposal to ask for time on a radial velocity instrument to then follow that planet up and confirm it by measuring the mass of that planet. And so that's how I use the radial velocity method, but I don't use it to actually discover planets. Microlensing is something that I've recently been getting into. It is similar to the transit method in that it looks for changes of brightness, but instead of looking for decreases of brightness, it looks for increases in brightness, and it's because of general relativity. It's like a really wild technique. And so in that case, I've just been starting to get into it, but because I started with the transit method, it's been a shift in perspective to use that type of technique. And direct imaging is something that I have not worked on or done any follow-up for, but yeah, I think then again, it's more you need to ask for time on telescopes to specifically get direct imaging observations, whereas the transit data is just so much more available and publicly accessible that it makes it a lot easier to use.
Excellent, thanks. And we'll go, I think our last question, unfortunately, will go to Brian, who's had his hand up for a little while. So go ahead, Brian.
Sorry. Thank you, Dr. for your interesting speech. I really appreciate it. My question is, when you're trying to figure out the composition of an atmosphere of exoplanets by observing the wavelength, would that be affected by the duplicate shift, or it doesn't matter because the graph will just move to the left or right in its original shape?
Sorry, it'll be affected by what?
The Doppler shift.
Oh, so because the planet is passing between you and the star, the Doppler shift only happens when something is moving towards or away from you. And so the light from that planet's atmosphere is over the time scale of the observations, it's not going to be looking a lot different, like as you observe it, because of the Doppler shift.
Okay, thank you. But can I ask a follow-up question?
Sure, go for it.
But isn't the planet and the solar system actually moving away from us as the universe is expanding?
It will be, but the amount of shift that occurs because of that is not going to be affecting our observations.
Okay, understood. Thank you so much.
And maybe I'll
Yeah.
just throw in one extra question from Brian and maybe try and combine with what Jazzy's getting at in the chat is in terms of the goal of finding habitable planets, is it to find intelligent life? And is there a possibility of discovering potentially Archaea-like entities on other planets?
Yeah, I mean, I think that the search for other Earths is something that, like, honestly speaking, speaks to our curiosity as human beings. It's not just a scientifically interesting question about like, oh, well, what are the specific conditions of life on another planet? It's a philosophically fascinating question. Like, are we alone in this universe? I think everybody has asked themselves that. And by finding planets, we're taking the very first steps to actually help answer that really big question. So it feels like a very profound question that, you know, as exoplanet hunters and exoplanet studiers, we can actually start to answer. So there's that perspective, like societally and culturally speaking, it feels like a really big question to be able to help answer. But then from, you know, practically speaking, yes, by looking for more planets that could potentially host life, they could actually have life living on that planet. And part of our what we want to do is understand how common that might be. Like, is life on another planet extremely rare? Can you have conditions on another planet's surface that look very different than what we see on Earth, but can nevertheless host life? And yeah, I think that would be one of the ultimate goals of being able to do this type of research.
Amazing. Thank you so much. So lastly, just please join me in thanking Dr. Michelle Kunimoto for a fascinating first seminar for Sci 113. Thanks, everyone.
Thank you.
Thank you.
Thank you.
Thank
Thank
you.
you.
Bye.
Thank you.
Thanks, everyone.
Thank you.
Thank you. Thank you.